Today we're going to continue with matrices and we're going to learn about the determinant of a 2 by 2 matrix, the adjoint of a 2 by 2 matrix, and ultimately how to find the inverse of a 2 by 2 matrix, right? So you may recall a 2 by 2 matrix is a matrix that has two rows and two columns. So say you have a matrix A, and let's say A is A, B, C, D. The determinants of this matrix, A, okay, the determinants of A, which is written as like a modulus A, okay, so two straight lines, two vertical lines, and A in between. That stands for the determinants of A when you're dealing with matrices. And that is found by subtracting the products of the diagonals, meaning AD take away BC. That's the determinant of the matrix where A is equal to A, B, C, D, right? So it's the difference of the products of the diagonals. So, for example, let's say we have a matrix A. A is equal to 3, 2, 1, 4. Then the determinant of A be equal to the difference of the products of the diagonals. So AD, which in this case is 3 by 4. So 3 times 4 minus 2 times 1. That would give me 12, take away 2, which is 10. So the determinant of A here is, right? So the determinant of a matrix, a 2 by 2 matrix, and that's all you need to know for this level, the determinant of a 2 by 2 matrix, is found by subtracting the products of the diagonals. So if you have a matrix A, and it's equal to A, B, C, D, where A, B, C, and D are real numbers, then the determinant is found by saying A times D minus B times C. And we write the determinant, well, this is what you call the modulus, right? So we write it like this, modulus A. In matrices, this stands for the determinant of A. Okay, so in this example, A is 3, 2, 1, 4. So the determinant would be 3 times 4, take away 2 times 1. Let's say we have another one. Say we have a matrix C. This matrix is equal to 4, negative 6, negative 2, 3. Well, the determinant of C, denoted by this, would be equal to 4 times 3, take away negative 6 times negative 2. Well, 4 times 3 is 12. Take away negative 6 times negative 2 is positive 12. And 12 take away 12 is 0. So the determinant of C here is equal to 0. And here is something that you have to learn. When the determinant of a matrix is equal to 0, it's called a singular matrix. So when the determinant is equal to 0, matrix is a singular matrix. Something to make a note of, guys. You need to know what is a singular matrix, right? So when, like in this one, the determinant was 10. When the determinant of a matrix is not 0, so like in this case, it's a non-singular matrix. When it is 0, the matrix is singular, right? So when it is not equal to 0, when the determinant is not equal to 0. So it could be any number, any negative number, any fraction, any positive number. then the matrix is non-singular. So in the first example, that was a non-singular matrix. And in this example, part B, sorry, with matrix C, C is a singular matrix because its determinant is equal to 0. So that's another example. So we have -2, the matrix B, which is -2, 1, 5, -3. The determinant of B, noted as this, would be equal to the difference of the products of the diagonals. So it will be -2 times -3, take away 1 times 5. So this would be -2 by -3 is +6, minus 1 times 5, which is 5. So the determinant of B here is 1. And it is a non-singular matrix because the determinant is not equal to 0. So I want you all to do a quick exercise for me. Find the determinants of each of these matrices, sorry. Find the determinant and state whether they are singular or non-singular. Please send it to me. I want to see your working. Write them down now. Right, so find the determinants of each of the following matrices here and state whether the matrix is singular or non-singular. Please write the matrix itself, then the determinant, like how it's done in the example above. Right, let me just do them very quickly. The determinant of A, I use a different color actually. The determinant of A would be 3 times 7. Oh my gosh. 3 by 7, take away 4 by 6. So that will give me -3. The determinant of B would be 4 times 3, take away 7 times 8, gives me -44. Number 3, determinant of C would be 9 times 4, take away 2 times 3. That gives me 30. And then the determinant of D would be 7 times 4, take away 2 times 14, which is 0. So all of them except D are non-singular, right? So this one is non-singular because remember, a non-singular matrix is one where the determinant is not 0. So all of these 1, 3, and 2 are all non-singular matrices because their determinants are not equal to 0. However, for 4, determinant of D is equal to 0, so he's the only one that's a singular matrix for him. All right? So now we're going to look at the adjoint of a matrix, a 2 by 2 matrix. Like I told you all, for this level, you only need to know the determinant and the adjoint of a 2 by 2 matrix. And all of this is building up to find the inverse of a matrix. So you're going to look at the adjoint of a 2 by 2 matrix. The adjoint of a 2 by 2 matrix, say you have a matrix A, given the matrix A equal A, B, C, D, then the adjoint of the matrix A written as A, D, J. Adjoint, short ADJ, short for adjoint, is found by simply swapping the first and this diagonal A and D. So D will come here and A will come here. So you switch positions with them and you change the sign of B and C. So again, to get the adjoint, you swap the leading diagonal, so A and D, and then you change the sign of the remaining elements. So let's look at that in an actual example. Let's say you have a matrix A. This matrix is equal to 7, 3, 1, 5. Well, A adjoint would be equal to, you swap 7 and 5, so you'll have 5 here and 7 here, and then you change the sign of B and C. So you change the signs of the remaining elements. All right. B, let's say we have another matrix B, and B is equal to -5, -2, -1, -4. Then B adjoint would be equal to, you swap the first and last positions. So this will become -4 and this -5 will go here. And you change the signs of the remaining two. So instead of -2, this will be +2. And instead of -1, this will be +1. Right? Pretty simple. Pretty simple. Let's look at one more. Here I have a matrix C. And C is equal to 3, -1, -7, 2. Well, the adjoint of C, written as CADJ for short, would be 2, 3. So I swap those and I change the signs of the remaining elements. So it'll be 1 and 7. That's it. That's the whole thing about the adjoint. So you do have to, it is easy, but you do have to be careful with your signs and you do have to memorize it because it's not given to you in your list of formulae. All right, let's look at, let me give you an exercise now. I'm going to write down some for you to try for me. say you have a matrix A. A is 3, 4, 6, 7. Gosh, if I said 6, 7 in like my one of my younger classes, they would just go off. E is equal to 4, 7, 8, 3. C is -2, 3, -4, 5. You do in the adjoint, you state in the adjoints of each of these. All right, try these for me, guys. Send it to me on WhatsApp, please, when you finish. Right, so the adjoint for A, adjoint, you swap 3 and 7, so that would be 7, 3, and then you change the sign of the remaining two, so -4 and -6. The adjoint for B, you swap the first and last terms. I said swap and then I wrote over the same thing. So right, 3, 4. Then you change the signs of the remaining ones. A C adjoint, change the positions here. So 5 will be here, -2 will come here, and you change the signs of the remaining ones. So this was 3, so it becomes -3, and this was -4, so it becomes 4. For part D, we'll have -5 and -7, and then +6, +4. And then E, last one, it'll be 4, -3, and then 2, 1. Right? So pretty straightforward, right, guys? It's just about remembering what the things mean. Like the fact that a adjoint means where you swap the leading diagonal and change the signs of the remaining two. And then the determinant is when you subtract the products of the two diagonals. So A times D, take away B times C. Right? So now we're gonna bring all of that together in stating the inverse of a matrix, right? Now, by the way, you can only find the inverse of a non-singular matrix. The inverse of a singular matrix does not exist, and you'll see why shortly. So now we're going to look at the inverse of a 2 by 2 matrix. And for starters, you could only find the inverse of a non-singular matrix. So you can only find the inverse of a matrix whose determinant is not equal to 0. Right, so if you have a matrix A, and A is A, B, C, D, then A inverse, written like this, A inverse is given as 1 over the determinant of A multiply by A adjoint. That's how you find the inverse of a matrix. So that's how you state the inverse of a matrix. And um, essentially that is, well, 1 over the determinant. Remember, the determinant is AD minus BC times the adjoint, which is, if the matrix is A, it'll be D, A minus B minus C. So this is the same thing, right? A inverse. the second part here, I just wrote out exactly what the determinant of A is and what is the adjoint of A. So let's look at an example. So let's say we have the matrix A, and A is 2, 3, 1, 5. And I would like to find the inverse of A. Well, firstly, the determinant of A would be 2 times 5, take away 3 times 1. That would give me 2 fives are 10, and 3 times 1 is 3, so 10 take away 3 is 7. The determinant is 7. And then the adjoint, A adjoint, is equal to, well, you swap the first and last, so that would be 5, 2, negative 3. You change the signs of the remaining 2, so that would be negative 3 and negative 1. And therefore, the inverse would be equal to, oops, not brackets as yet, 1 over the determinant, which we found as 7. So 1 over 7 times 5, negative 3, negative 1, 2. And you can now multiply throughout by the scalar. So this means you have 1/7 times the adjoint literally means that you have to do your scalar multiplication here, which means that you multiply 1/7 by each term inside of or each element of the matrix. So that would give you, well, 1 over 7 times 5 would be 5 over 7. Negative 3 times 1 over 7 will be negative 3 over 7. Negative 1 times 1 over 7 is negative 1 over 7. And then 2 times 1 over 7 will be 2 over 7. And this is your inverse, right? So the determinant, the inverse of A is found by taking 1 over the determinant of A and multiplying it by the adjoint of A. So you can do it separately like this, where you write out what is the determinant and then what is the adjoint and then put it together like how I did it here. Or alternatively, you can just put it directly into like the second part, the second representation here. So I could have said, well, if A is um 2, 3, 1, 5, then A inverse will be 1 over A times D. So that would be 2 by 5, take away 3 by 1. Let me write this better. Yeah, so it's 1 over that, multiply by the adjoint. So that would be 5, 2, negative 3, negative 1. And then I just simplify it right there. So that would be, well, this would give me 1 over times 5 is 10. 3 times 1 is 3. So 10 take away 3 is 7. So that'll be 1 over 7 times 5 minus 3 minus 1, 2. Then I multiply out the scalar by the matrix, and I will get the same thing. 5 over 7, negative 3 over 7, negative 1 over 7, or 2 over 7. However you want to do it is fine. When I do it, I typically do the write out the determinant, the adjoint, and then put it together as the inverse. But you could do it like this as well. It's the same thing. All right, let's do another example. Let's say I wanted to find the inverse of B, where the matrix B is given as negative 4, 5, 1, negative 2. I'm going to write over this 5. It kind of looks weird. Right. So recall that inverse of B is equal to 1 over the determinant of B times B adjoint. So let's do the determinant of B. The determinant of B is equal to -4 times -2. Take away 5 times 1. So this would be -4 times -2 is 8, positive 8. And then 5 times 1 is 5, so that will be 8 take away 5, which is 3. So the determinant of B is 3. So I have that piece of information now. And then I do B adjoint. Well, I guess I could just go straight to listing it. Here, B inverse. E inverse is therefore equal to 1 over 3, because that's the determinant of B, by B adjoint. And B adjoint, what we do is we swap leading diagonal. So -2 will come here instead, and -4 will go here. And then I change the signs of the remaining values. So this will be -5, -1. That gives me, when I multiply throughout by the scalar 1/3, 1/3 times -2 will be -2 over 3. -5 times 1/3 will be -5 over 3. -1 times 1/3 is -1 over 3. And then -4 times 1/3 will be -4 over 3. And that is my B inverse. -2 over 3, -5 over 3, -1 over 3, and -4 over 3. That's another one. Let's say I wanted to find let's say I have the matrix C, and C is equal to, um, one moment. C is equal to 7, 2, 14, 4. All right? Again, recall that C inverse is equal to 1 over the determinant of C times the joint of C. Right? Well, first things first, let's do the determinant. The determinant of C would be equal to 7 times 4, take away 2 times 14. This would give me 28, and 2 times 14 is also 28. 28 take away 28 is 0. But you cannot have 0 in the denominator. You cannot divide by 0. It is does not exist. You're not able to divide by 0. And this is why the determinant, sorry, the inverse of a singular matrix does not exist, because you'll end up with 1 over 0, right? Because if the determinant is 0, you'll end up with 1 over 0 times the adjoint. But you cannot find 1 over 0. And that's why the determinant of a singular matrix, not its determinant, sorry, I keep saying that. The inverse of a singular matrix does not exist. That is something that you need to make a note of, right? You cannot find the inverse of a singular matrix. This is why, because you'll end up with 1 over 0, and you cannot actually divide by 0. All right, at this point, I am going to ask you now to find the inverse of a couple of matrices for me. Which, of course, I would like you to send across on WhatsApp. Even if I start to write these solutions and you didn't finish, just send what you have. Right. So you're gonna send me these. I'm gonna do these. Finding the inverse of each of the following. And recall, just gonna put this on the bottom here for you. Recall that the inverse of A is equal to any matrix A. I'm just using A. 1 over the determinant of the matrix multiplied by the adjoint of the matrix. I'm gonna do the first three. Right? So first one is A is equal to 3, 4, 6, and 7. Oh my gosh, the 6, 7 thing is haunting me. So the first thing you do, recall A inverse is equal to 1 over the determinant of A multiplied by A adjoint, right? So the determinant of A is the front of the products of the diagonals. So the determinant of A will be 3 by 7 minus 4 by 6. And that gives me 3 by 7 is 21. 4 times 6 is 24. So the determinant of A is -3. All right. So now let's put it together. For the inverse of A will be 1 over the determinant. So that's 1 over -3. And 1 over -3 is the same as saying -1/3, right? So 1 over -3 is the same as saying -1/3. All of that by the adjoint, which would be you swap 7 and 3, and then you change the signs of 4, so that'll be -4 and -6. And now you multiply it out. So that would be -1/3 by 7, which will be 7 over 3. Well, -7 over 3. Negative 1/3 by -4 will be positive 4 over 3. -1/3 by -6. I'm just going to show you all out here. 1/3 by 6 would be 3 into 3, 1, 3 into 6, 2. So that would be, and a negative by negative is a positive. So this will be +2. And then -1/3 by 3. Well, 1/3 by 3 will be 1. But since it's negative, 1/3 by +3, it's going to be -1. So A inverse is equal to -7 over 3, 4 over 3, 2, -1. Let me get number three. Right. Number three is the matrix C is given as 9, 2, 3, 4. The first thing, let's find the determinant of C. That would be 9 times 4, take away 2 times 3. This 9 fours are 36, 2 times 3 is 6. So the determinant of C is 30. Make sure. 9 times 4, take away 2 times 3. Yes, 30. So then, um, C inverse is found by 1 over the determinant, so 1 over 30 times C adjoint. So that would be 4, 2, 4 negative 2, sorry, negative 3, 9. You swap the leading diagonal and change the sign of the remaining two elements. So that would be negative 2 and negative 3, and then you swap 4 and 9. All right, good. And now let's multiply throughout by 1 over 30. So 4 times 1 over 30 times 4 is 2/15. Negative 2. 1 over 30 times negative 2 is negative 1 over 15. Negative 3 times 1 over 30 would be negative 1 over 10. And then negative 1 over 30 times 9 is 3 over 10. So if you didn't get these, please check it over, see where you went wrong. All right, the next one, number 4, this is E. E is given as 4, negative 3, 2, negative 1. First thing, let's find the determinant of D. That would be 4 times negative 1, take away negative 3 times 2. 4 by negative 1 is negative 4 minus, well, negative 3 times negative 3 times 2 is negative 6. So this would be negative 4 plus 6, which is positive 2. So the determinant of D is positive 2. All right. So therefore, the inverse of D inverse is 1 over 2, so 1 half by, we swap the adjoint, right? So we swap the leading diagonal, so that'll be 1, 4, and you change the signs of the remaining element. So that'll be 3, because it was negative 3 here. So it becomes 3, and then this was positive 2, so in the adjoint it will be negative 2. And then we just multiply throughout by a half. So D inverse would be equal to 1 times a half, which is a half, 3 times a half, which is 3 over 2. Negative 2 times a half is negative 1, and and then 4 times a half is 2. And that's your D inverse. A half, 3 over 2, negative 1, 2. Number 5, E, we had E given 5, negative 3, 4, negative 2. So the determinant of E is 5 times negative 2 minus negative 3 times 4. So this would be 5 times negative 2 is negative 10. Negative 3 times 4 is negative 12. So this is negative 10. Negative by negative is a positive. So negative 10 plus 12, which will be 2. So the determinant of E, just like the determinant of D, is also 2. So therefore, E inverse, which is 1 over the determinant, so 1/2, by the adjoint of E. So we swap -2 and 5, we swap positions, we change the signs of the remaining elements in there. And now we multiply throughout by 1/2. So 1/2 times -2 is -1. 3 times 1/2 is 3 over 2. -4 times 1/2 is -2. And then 5 times 1/2 is 5 over 2. Tristan, you saw I think you had some signs. I think the numbers were correct, but the signs were off. Did you see them? Were you able to spot them?
Yeah, yeah, Miss, I did.
Okay, cool. All right. And now the last one, number 6. Amisha, how it's going there? Follow it?
Yeah, Miss Saffron.
F is 4 minus 1, 7 minus 6. Right. So first thing, we find the determinant of f, which would be 4 times -6 minus -1 times 7. So 4 times -6 is -24. And then minus -1 times 7 is -7. So this will be -24 plus 7, which is -20. -24 plus 7 is -17. So therefore, F inverse would be -1 over 17 times the adjoint of F. So you swap -6 and 4 and change the sign of the remaining values. All right, and now we multiply throughout. So Amisha, you had up until this point, the first one that you sent me, and that was correct, right? The only thing now is to multiply each element inside the matrix by 1 over the determinant. That's what I was trying to explain in the WhatsApp.
Oh, okay. Okay, yeah, Miss.
Right? So you had up until this point, which is correct, right? It's correct. But now you just have to multiply out those
Multiply it
brackets.
to get the answer.
Yeah,
Okay, no
correct.
problem.
The final answer. So -1 over 17 times -6 will be positive 6 over 17. -1 over 17 times 1 will be -1 over 17. -1 over 17 times -7 will be positive 7 over 17. And then 4 times -1 over 17 will be -4 over 17. Jazara, I think I glimpsed some errors in yours, but I'm really not sure. But um, just check it back for me, okay? With the solutions that I just put. Mhm. And Evan, I didn't check your answers as yet, so now going to look at it.
All right, Miss.
So the identity of a 2 matrix. Now, in regular math with regular numbers, we call the additive identity, for instance, the additive identity is 1. No, not 1, 0. The additive identity 0, because if you have a number A, you add 0 to it, you'll get back A, right? Now, the multiplicative identity is 1, because when you multiply A by 1, you get A, right? So The identity matrix in terms of a 2 by 2 matrix is, well, actually, before we reach there, if you multiply A by its inverse, or the inverse of A is 1 over A, you'll get 1, right? So when you multiply A by its inverse, you get the identity, the multiplicative identity. So you get back 1 because A times 1 over A would be A over 1 times 1 over A, and these will cancel, right? So in the same way, when you multiply a 2 by 2 matrix by its inverse, you get the identity matrix. Just like when you multiply a regular value A by its inverse, you'll get 1. Well, when you multiply a matrix by its inverse, you'll get the identity matrix. And the identity matrix, well, the identity of a 2 by 2 matrix is given as 1, 0, 0, 1. That is the identity matrix. If you multiply any matrix by 1, 0, 0, 1, you'll get back the matrix. So let's put it to the test, right? So um, I'm going to use one of the examples from before to just show you. So if I have, so A times its inverse, A inverse is equal to the identity matrix. So using an example from what we did just now, um, let's say I have the matrix A, and A is equal to 5, -3, 4, -2. Well, A times the identity matrix will give you back A. Watch. 5, -3, 4, -2 times 1, 0, 0, 1. That would give me, I don't know if you'll remember, matrix multiplication, row times column, and then row times column. So row times column, row 1 times column 1 would be 5 times 1, which is 5, plus -3 times 0. So that would just give me 5. 5 times 0 is 0. -3 times 1 is -3. 4 times 1 is 4, plus -2 times 0, which is 0. So this will just be 4. 4 times 0 is 0, plus -2 times 1 is -2. So as you can see, A times the identity matrix is itself A, right? Now, let's find the inverse of A. Well, we did this one before, right? This one was actually number 5 in the exercise. I had it as E, but this time I just wrote it as A. So I already know what the inverse of A is. A inverse is equal to -1, 3 over 2, -2, 5 over 2. That's the inverse of A. And I want to show you that multiplying A by its inverse will give you the identity matrix, right? So do it. Now, one thing to remember, see, A times A inverse. Well, that would be 5, -3, 4, -2 times -1, 3 over 2, -2, 5 over 2. Right, so let's do it. Let's see. So you're going to do row by column. So this would be 5 times -1 plus -3 times -2. That's the first value that would go there. Sorry, I don't know. I made this really thin and now it's difficult to see. And then we have row 1 by column 2. So that would be 5 times negative, no, 5 times 3 over 2 times plus, sorry, negative 3 times 5 over 2, right? Remember, row 1 by column 1 would be this one here. So 5 by negative 1 plus negative 3 by negative 2. And then same row 1 by column 2 would be 5 by 3 over 2 plus negative 3 by 5 over 2. And then on the bottom, you have row 2 by column 1. So 4 by negative 1 plus negative 2 by negative 2. And then row 2 by column 2. So that would be 4 times 3 over 2 plus negative 2 times 5 over 2. Note this out. Now, if you can't remember how to do the matrix multiplication, I suggest watching over that video, right? So let's see. That would give me, well, 5 times negative 1 is negative 5 plus negative 3 times negative 2 is positive 6. So negative 5 plus 6 is 1. And then 5 times 3 over 2 is 15 over 2 plus negative 3 times 5 over 2 will be negative 15 over 2. So negative 15 over 2 plus negative 15 over 2 is 0. And then on the bottom, 4 times negative 1 is negative 4. And negative 2 times negative 2 is positive 4. Negative 4 plus 4 is 0. And then 4 times 3 over 2 would be 12 over 2 plus negative 2 times the 5 over 2 will be negative 10 over 2. Wait, there's a mistake because 12, no, never mind. 12 over 2 is 6 and negative 10 over 2 is 5. So 6 take away 5 is 1. So there's no mistake. So there you go. And 1, 0, 0, 1 is the identity matrix. So this is the proof that A times its inverse is equal to the identity matrix 1, 0, 0, 1. Right, guys? So that is a rule to remember. So let's go over the main things that we learned today. The first thing that we looked at was the determinant of a 2 by 2 matrix, which if you have a matrix A given as A, B, C, D, the determinant of that matrix will be A times D minus B times C, right? So it's the difference of the product of the diagonals. So A by D minus B by C. So that's the determinant of a matrix. On the same topic of the determinant of a matrix, we saw that when the determinant of the matrix is 0, it is known as a singular matrix. And when the determinant of the matrix is not 0, the matrix is non-singular. You have to be able to tell when a matrix is singular and when it is non-singular. Next, we looked at the adjoint of a 2 by 2 matrix, which is essentially when you change the positions or swap positions with the leading diagonal. So you swap the positions of A and D, and then you change the signs of B and C. So if the matrix is A, which is A, B, C, D, the adjoint of A adjoint is B minus B minus C minus A. So that was the next thing that we learned. And then we put it together to talk about the inverse of the matrix. So the inverse of the matrix is given as 1 over the adjoint of the, sorry, 1 over the determinant of the matrix multiplied by the adjoint of the matrix. So therefore, if you have a matrix A whose well, A is denoted by A, B, C, D. Then it'll be 1 over AD minus BC. That's the actual determinant of the matrix A by the adjoint. So D minus B minus CA. So we put it all together to find the um the inverse of the matrix, right? We did a few examples on that. We also saw that when you have a singular matrix, you cannot actually find the inverse because the determinant will be zero and the part of the inverse is 1 over the determinant, and you cannot ever have zero in the denominator. Why? Because you cannot divide by zero. So therefore, the inverse of a singular matrix does not exist. You can only find the inverse, sorry, of a non-singular matrix. And then we found the inverse of these. And now I just showed you that the identity of a 2 by 2 matrix is given as 1, 0, 0, 1. So this is the identity matrix. It means that if you multiply A by its inverse, you will get the identity. And similarly, let me write this down as well. Similarly, A times the identity is equal to A. So any matrix multiplied by the identity matrix will give you back the original matrix. Likewise, a matrix multiplied by its inverse will give you the identity matrix. And we proved that over here. So I showed you that A times the identity will just give you back A, and then A times A inverse will give you the identity matrix. And all of these are fundamental for the next thing that we're going to do next week, which is solving simultaneous equations using a matrix method. I'm not going to start that now. I think it's too late, but I think that so far, based on what I've seen, everybody seems to be okay with it. Just a few mistakes with signs here and there, but otherwise, your work looked good today. So next week, we're going to solve simultaneous equations using a matrix